You run the exact same software build on, the exact same code repository you used yesterday.
Right.
And yesterday, that build took, say, 384 seconds.
Hmm.
But today, it takes 411 seconds. Or you're running a CNC lathe.
Touching absolutely nothing on the control panel.
Exactly. Touch nothing. You use the exact same batch of steel, but part A comes out at 10.01 millimeters, and part B comes out at 9.98 millimeters.
Yeah.
Or you look at your weekly error rate, and it just inexplicably bumps up from like 2.6% to 3.2%.
And no one did anything.
Right. Not a single input was deliberately altered, no code was changed, no settings were tweaked,
Yeah.
and yet the outputs just kind of wander.
Yeah.
So welcome to our deep dive on the universally maddening reality of doing the exact same thing twice.
It really is the defining frustration of anyone who builds or manages anything. I mean, you design a system to be deterministic. You expect precision.
Yeah, you want X to equal Y every time.
Right. And the universe just hands you a smear of probabilities instead. That wandering output, that's what we call variation. And no process, no matter how tightly controlled it is immune to it.
And I feel like the thing that keeps managers and, engineers up at night is looking at that smear, like looking at that 411-second build time and trying to answer just one question.
Is this normal?
Exactly. Is this fluctuation just normal noise in the system, or is it, a critical signal that something is fundamentally broken?
Because if you get that answer wrong, you are going to waste time, you'll waste money, and morale just tanks.
Yeah.
And honestly, worse than that, you will actively degrade the system you're trying to fix. So our mission for this deep dive is to really unlock the discipline designed specifically to answer that exact question.
Which is Statistical Process Control, or SPC.
Yes, SPC.
Yeah.
We are going to dig into the physics of variation, how to mathematically decompose it, and how to build frameworks that tell you exactly when you need to tear a system apart and when you just need to, sit on your hands and leave it alone.
But before we even get to the math, we have to lay down the golden rule of process engineering. I mean, it's the sequence that governs absolutely everything else.
Stability first, capability second.
Stability first, capability second. We can't even begin to ask if a process is good enough until we prove that it's stable.
And people almost always reverse that order, right?
Constantly.
A customer or a manager will walk up to a new manufacturing line or a new software pipeline and immediately ask, is this capable of meeting our requirements? They just want to grade the output right away.
Right. They want the report card on day one.
Exactly. But if a process is unstable, if it behaves unpredictably from 1 hour to the next, it doesn't actually have a single unified distribution. You aren't measuring a process.
You're just measuring random events.
Yeah, a series of random, totally unconnected events.
It's kind of like trying to calculate the average speed of a driver who is just having a seizure at the wheel. The number you get is mathematically real, sure, but it has zero predictive power for the next 10 miles.
That is a terrifying but incredibly accurate analogy. If a process has no single identity, forecasting its future is just guessing. You have to stabilize the system to give it a predictable identity.
And only then do you judge it.
Right, only then. So to get to that baseline of stability, we have to look really closely at the variation itself. The foundational insight of SPC, which was actually pioneered by this guy Walter Shewhart at Bell Labs in the 1920s, is that variation isn't just one monolithic thing.
It splits into two totally distinct categories.
Yes, and they demand completely opposite managerial responses.
Okay, so let's break those down. The first category is common cause variation. This is the random, inherent fluctuation of a process that is working exactly as it was designed to work, right? Like the baseline noise.
Exactly.
Yeah.
Think about all the tiny, unidentifiable factors operating in the background of any physical or digital system.
Like what?
Ambient humidity, microscopic inconsistencies in your raw materials, slight voltage fluctuations, background network traffic, even just the basic hum of measurement noise. None of those factors are individually identifiable.
And you couldn't track them all down even if you wanted to, right? It would bankrupt you to try and stabilize the ambient humidity of a massive factory to the 5th decimal place just to stop like a single millimeter of drift.
Oh, you'd spend millions to save pennies. It's ridiculous. But when you aggregate all those tiny invisible factors, they combine to create a stable, predictable distribution.
The bell curve.
Yes, the
Yeah.
classic normal distribution. In a healthy process, that bell curve is the fingerprint of common cause variation. It tells you the process is doing exactly what its design allows it to do.
Okay, so that's the noise. Then we have the second category, which is special cause variation. Sometimes people call this assignable variation.
Yeah, assignable is the other term, because you can assign it to a specific cause. This is a fluctuation tied to a specific identifiable event that sits completely outside of normal operation.
Right, so this is the sudden shock to the system.
Exactly. A machine tool physically chipping and wearing past its edge. An untrained operator taking over the afternoon shift and just doing things in the wrong sequence. Or, a sudden dependency outage in your cloud infrastructure.
So it isn't a tiny background fluctuation at all. It's a discrete event.
And it shows up in the data completely differently. You don't see a gentle bell curve.
You see a massive spike.
Yeah, a sudden violent spike. Or a sustained, obvious shift away from the historical baseline. But the reason we care so deeply about classifying variation into these two buckets isn't metaphysical, it's fiercely operational.
Right, it's about figuring out who has the authority and the responsibility to actually do something about it.
Precisely. If you see a special cause, a spike on a chart that demands immediate local investigation, it demands detective work.
So someone on the floor.
Yeah, an operator or an on-call engineer needs to go out, find the broken tool or the bad code commit, remove it, and basically restore the process back to its baseline. That is a local operational task.
But common cause variation is entirely different, right? Because it's baked into the DNA of the system. An operator on the floor literally cannot fix common cause variation.
They physically can't. If the baseline noise of your system is simply too wide for your customer's liking, the only way to narrow it is by tearing up the floorboards.
You have to change the machinery.
Exactly. You have to upgrade to higher grade raw materials. You have to rewrite the fundamental architecture of the software. That requires real capital allocation. It is a management level, engineering level decision.
I want to ground this in a physical analogy for a second, just because I think it highlights how the exact same physical factor can be a common cause in one context, but a massive special cause in another.
Oh, sure.
So think about ambient temperature fluctuations. Say you're running a massive shipping warehouse, and the temperature rises, 5 degrees in the afternoon. That is just baseline common cause noise. It might slow the workers down slightly. It might affect forklift battery life by a tiny fraction of a percent. But it's just the aggregate hum of the warehouse. You don't investigate it.
Right, you expect it. It's just part of the system's identity.
But take that exact same 5-degree temperature fluctuation and put it inside a highly controlled laser calibration lab.
Oh, wow. Yeah.
Suddenly, it is a catastrophic special cause event.
Yeah.
It will physically warp the lenses, expand the metal mounts, and completely ruin the calibration.
Total disaster.
Right. It demands immediate local investigation. Someone needs to figure out why the HVAC system failed, fix it, and reset the room. The physical root cause, the 5 degrees, is identical, but the operational context dictates an entirely different response.
That is exactly the core of process management. Diagnosing the situation correctly based on context. Because if you misdiagnose the type of variation you're looking at, you are going to commit one of the two cardinal sins of management.
Okay, so let's get into the sins.
You will either tamper with a stable system, or you will be totally blind to a broken one.
So I guess we should dive into tampering first, right? Because I feel like that's the one everyone does, and they usually do it while genuinely trying to do a good job.
Oh, absolutely. Tampering is treating common cause variation as if it were a special cause.
So overreacting to noise.
It is overreacting to noise, and we see this constantly in corporate environments. A manager pulls up the weekly sales dashboard, sees a 2% downtick compared to last week, and demands a full written explanation from the sales team.
Or an operator on a manufacturing line measures a part, sees it's a fraction of a millimeter off target, and immediately starts turning dials and adjusting the machine settings to compensate.
Oh, exactly.
But wait, intuitively, that sounds like good management,
Yeah.
right? Like you have an attentive operator, you see an error, you correct it. Why is that a sin?
Because if that 2% downtick or that fractional millimeter was just random common cause noise, then the system hasn't actually shifted. It's just vibrating within its normal parameters.
Right.
By reacting to it, by demanding new sales strategies or physically turning a dial on a machine, you are injecting a brand new physical force into a random sequence. You are mathematically adding variation to the system.
Okay, this brings up W. Edwards Deming and the famous funnel experiment, which I think is one of the most elegant statistical demonstrations ever devised.
It really is.
Walk us through the physical mechanics of what actually happens when you try to overcorrect like that.
Sure. So Deming used a really simple physical setup. You have a funnel mounted above a table, and you drop a marble through it. trying to hit a target drawn on the table below.
Okay.
Now, no matter how perfectly you set up the funnel, the marbles will never hit the exact dead center every single time.
Because of the noise.
Right. Microscopic vibrations, air currents, slight irregularities in the glass of the marbles, that creates a natural circular scatter around the target. That scatter is your baseline common cause variance. So let's call that baseline variance sigma squared.
Okay, so the system has a natural variance of sigma squared. Now the tampering begins.
Right. Let's say an overly attentive operator drops a marble and it lands 1 inch to the right of the target.
Okay.
The operator thinks, the system is biased to the right. I need to fix this. So for the very next drop, they physically move the entire funnel 1 inch to the left.
Trying to perfectly compensate for the previous error.
Exactly.
But because that initial 1-inch error to the right was purely random noise, the next marble was going to fall randomly anyway. The system wasn't biased, it just produced a random outcome.
Exactly. The next marble is subject to the exact same inherent random scatter, but now the operator has added the physical movement of the funnel to the equation. Mathematically, the variance of the marble dropping is statistically independent from the variance of the operator moving the funnel.
Right, they aren't tied together.
And a core law of statistics is that the variances of independent events add together.
Oh, wow. So you take the inherent randomness of the marble, which is sigma squared, and you add the variance of the funnel adjustment, which is also sigma squared, because the adjustment is based directly on the size of the last random error.
You get 2 sigma squared.
So doubles.
Yes. By trying to eliminate the error, the operator has literally doubled the variance of the system. The scatter of the marbles will get wider and wider the more they try to chase the noise.
If you are driving on an icy road, this is the exact physics of a fishtail.
Oh, that's a great way to look at it.
Right, like you feel the back of the car slip a tiny bit to the right. That slip is just the baseline noise of driving on ice. If you hold the wheel steady, the car will usually resolve it.
Just let the system work.
But if you panic and jerk the steering wheel to the left to compensate, you aren't fixing the slip. You're introducing a massive new physical vector into a random system. Your overcorrection throws the car wildly to the left, so you jerk it right, and every microadjustment amplifies the fishtail until you are in a ditch.
That is exactly tampering. Overcorrection destroys stability. Now, the second cardinal sin is the mirror image of tampering.
Which is blindness.
Right, blindness. This is when you treat a genuine special cause as if it were just common cause noise.
So averaging away a real signal.
Exactly. You see a massive sustained spike in API latency on your software dashboard, but instead of investigating what code deployment just happened, you shrug, say, oh, tech is just glitchy today, and you let that massive spike roll into the monthly average.
You completely ignore the fact that, a critical database index was just accidentally deleted.
An economic cost of blindness is terrifying because every single defective part that rolls off the line or every single frustrated customer who abandons their shopping cart due to latency, that is a direct cost incurred between the moment the system broke and the moment you finally wake up and realize it wasn't just noise.
So SBC, as a discipline, exists entirely to navigate the razor's edge between those two sins.
Yes. It is an economic decision procedure. You are trying to build a mathematical threshold that balances the cost of tampering against the cost of blindness.
But you can't build a mathematical threshold without data. And what you choose to measure entirely dictates whether you can actually spot the signal hiding in the noise. It feels like when we look at process data, we are basically choosing between a low-definition camera and a high-definition camera.
That's exactly what it is. Process data arrives in 2 distinct forms. The first, and historically the most overused, is attributes data.
Okay, what's that?
This is categorical data. It's count data, pass or fail, good or defective. Did the software build succeed or did it fail?
It is incredibly low resolution. It just summarizes an outcome.
Right. It discards an immense amount of information right at the point of measurement. If a customer needs a machined part to be 10 millimeters and they will accept anything between 9 and 11, an attributes measurement just tells you, yes, the part is inside that window.
It doesn't tell you if the part was a perfect 10.0 or barely passing 10.99.
Exactly. Because it throws away all that nuance, you need massive sample sizes just to detect a trend. If a system starts drifting, attributes data won't warn you until the system has degraded so badly that it starts physically producing defects.
So you might need to test 50 or 100 units
Yeah.
before the math can confidently tell you that the failure rate has shifted.
Which is why we vastly prefer the second type, variables data.
The high-definition camera.
Extremely high definition. This is continuous measurement, length in millimeters, voltage, API latency in exact milliseconds, time to complete a task in seconds.
And because it's continuous, every single measurement tells you exactly where the process is centered and exactly how much it spreads.
Right. Because of that richness, variables data gives you early warning capabilities. You can watch a cluster of measurements slowly drift from 10.1 to 10.3 to 10.5. You can spot the trajectory of a failure long before a single defective unit is ever produced.
And you can do it with tiny sample sizes.
Yeah.
You don't need 100 parts. You can spot a shift with just like 3 to 5 consecutive measurements.
Yeah, the math works beautifully on small samples.
But this raises a massive question for modern tech teams. If variables data is so vastly superior, why do software teams rely so heavily on attributes data? Like, you look at an engineering dashboard, and it's all failed deployments per week, or count of escaped bugs. It's all just pass-fail.
It comes down to friction and default settings. Counting failures is mathematically easy. A deployment either fails or it succeeds. Anyone can understand that metric. Furthermore, modern logging tools often just spit out error counts by default.
Right, it's out of the box.
Exactly. To capture variables data, to track the continuous distribution of deployment durations, or to analyze the exact distribution curves of query latencies, that requires a slightly higher level of statistical maturity and deliberate instrumentation.
You have to build it on purpose.
Yes, but upgrading a team's observability from pass-fail attributes to continuous variables of measurement is one of the highest leverage investments an engineering organization can make. It unlocks the ability to see the system's underlying physics rather than just tallying its casualties.
Okay, so let's assume we've made that upgrade. We are collecting rich, continuous variables data. We don't just dump it into a massive spreadsheet and average it all together, though. To make SPC work, we have to isolate the noise from the signal using a technique called rational subgrouping.
Yeah, rational subgrouping is essentially the experiment design of process monitoring. You collect your data in small, logical, time-bound batches.
How does that work in practice?
For instance, instead of taking one part every hour for 5 hours, you pull 5 consecutive parts off the machine right at noon. That tight cluster of 5 is your rational subgroup.
The logic here is brilliant. By pulling those 5 parts back to back, you are virtually guaranteeing that no special cause, no sudden shock to the system, had time to occur during the collection.
Right, the machine didn't degrade in those 3 seconds. The operator didn't change.
Therefore, any variation you see inside that tiny 5-part subgroup must be purely common cause baseline noise. You have successfully captured the baseline hum of the system in a bottle.
And if a special cause does hit the system, it will likely happen between the time you pull the noon subgroup and the time you pull the 4:00 p.m. subgroup. This sets up the mathematical engine of SPC, the sum of squares decomposition.
Let's really break down how this works. I know sum of squares sounds intimidating.
It sounds like a grad school nightmare, but it is conceptually very elegant. The total variation across all the data you collected all week can be sliced into 2 distinct buckets.
Okay, bucket 1.
Bucket 1 is the within subgroup variance. We look at the scatter inside each of those tight little 5-part batches. We average that scatter across all the batches. This gives us a highly accurate mathematical estimate of the system's unavoidable background noise.
So bucket 1 is the noise. What's bucket 2?
Bucket 2 is the between subgroup variance. Now, we totally ignore the individual parts. We just look at the average of the noon batch, the average of the 4:00 p.m. batch, and the average of the 8:00 p.m. batch. We measure how much those batch averages wander away from each other over time.
So we are separating the internal wiggle of the parts from the overarching journey of the process.
Exactly. And then we compare the two using the F ratio,
The F ratio.
which is simply a fraction. The numerator is the between subgroup variance, how much the process is wandering over time. The denominator is the within subgroup variance, the inherent baseline noise.
Okay, so if the system is perfectly stable, If nothing episodic has happened, those batch averages should really only wander by an amount dictated by the baseline noise.
Right.
So the numerator and denominator are roughly equal.
Exactly. If the wandering is just caused by background noise, your F ratio will hover around 1.0. It mathematically proves the system is stable.
But let's say a cutting tool shatters at 2.0 CPM.
Right, a special cause.
The 4.0 PM subgroup and the 8.00 PM subgroup are going to be machined much thicker than the noon subgroup. The averages of those batches will leap upward.
And so the numerator of our F ratio, the between subgroup variance, explodes. Meanwhile, the baseline noise in the denominator stays the same because the parts are still tight to each other within the broken state.
Suddenly you run the math, and your F ratio isn't 1.0 anymore. It's like 45.
Yes. The mathematics are formally declaring the means of your subgroups are wandering 45 times more than your baseline noise permits. Something external has hijacked this process.
It isolates the signal from the noise with absolute mathematical clarity.
Beautiful, really.
So we have irrational subgroups. We separated the noise from the signal. Now we have to operationalize this. We have to give the people running the process a visual tool that tells them exactly when to act.
We build a control chart.
The control chart.
The control chart takes all of this theory and just puts it on a screen. You take a piece of graph paper. The horizontal axis is time. The vertical axis is your measurement. Let's say it's the average diameter of your rational subgroups.
Yeah.
You plot those subgroup averages over time as a series of dots.
Okay. Then you draw a center line straight across the chart, representing the historical mean of the process.
Yep.
And above and below that center line, you draw the two most important lines in process management, the upper control limit and the lower control limit.
These limits bracket the expected variation. If a dot lands inside the limits, you presume it is just common cause noise.
You do not touch the system.
You avoid tampering. But if a dot lands outside those limits, the math is telling you that a special cause has occurred. You must go investigate.
You avoid blindness.
Exactly.
So the entire economic balancing act, the avoidance of tampering and blindness, comes down to exactly where we physically draw those two lines. How far away from the center line do we place them?
The universal standard established by Shewhart a century ago is the mean plus or minus 3 standard deviations. Mu plus or minus 3 sigma.
Why 3 sigma, though? I mean, I've seen data scientists argue for 2 sigma because it detects shifts faster. I've seen people argue for 4 sigma to avoid bothering engineers with false alarms. Why has 3 sigma survived for 100 years?
Because it strikes an incredibly robust economic compromise, specifically when you calculate the false alarm rate. If you assume the baseline noise follows a normal distribution, the math of the bell curve tells us that 99.73% of all data points will naturally fall within 3 standard deviations of the mean.
Which means only 0.27% of points will fall outside those lines purely by random chance.
Exactly. If we invert that probability 1 divided by 0.0027, we get roughly 370. This is called the average run length, or ARL.
Average run length.
Right. It means that if you set your limits at 3 sigma, a perfectly stable system will only trick you into a false alarm once every 370 data points.
Okay, so if you are pulling 1 subgroup a day, you will only chase a ghost once a year. That is a very tolerable level of tampering.
Right.
But what if we set it at 2 sigma?
If you set your limits at 2 sigma, about 5% of your normal data falls outside the lines. Your ARL drops to 20. Yeah. You will get a false alarm every 20 data points. You will be stopping the line, waking up engineers in the middle of the night, and tampering with a stable system almost weekly. The operational cost is devastating.
Okay, so tighter limits cause tampering. What if we widen the limits to 4 sigma to make absolutely sure we never get a false alarm?
Well, you eliminate false alarms almost entirely, but you induce massive blindness. At 4 sigma, the limits are so wide that if a real moderate special cause hits the system, say the mean shifts by 1.5 standard deviations, the new shifted data will still mostly fall inside your massive 4 sigma limits.
It could take weeks or months for a point to randomly trigger an alarm, and during that entire time, you are shipping defective product.
Exactly. 3 sigma is the sweet spot. It minimizes false alarms while maintaining enough sensitivity to catch real disasters quickly.
Okay, so we've established these 3 sigma limits based on what the process naturally does. But what if the customer doesn't care what the process naturally does? What if they demand tighter tolerances? This leads us directly to the absolute most dangerous classic beginner's error in all of SPC. It is the conflation of control limits with specification limits.
It is the root cause of so much organizational dysfunction, I can't even tell you. Control limits, as we just established, are calculated entirely from the internal mathematics of the process data itself, mu plus or minus 3, sigma.
Right.
They describe the reality of the physics on the ground. We call this the voice of the process.
The process doesn't care about your business goals. It just tells you how much it naturally vibrates.
Right. But specification limits are entirely different. The lower and upper specification limits, LSL and USL, are externally imposed boundaries. They are the contract. They are the blueprint.
They are the service level objective that says, 99% of web requests must load in under 300 milliseconds.
Exactly. They describe what is wanted. They are the voice of the customer.
So the two kinds of limits have absolutely no mathematical relationship to one another.
None. One is driven by physics, the other is driven by desires. And yet, day after day, people take their control charts, which show the natural variation of their system, and they literally draw the customer specification limits right over top of them.
Which is a complete category error.
Completely.
A process can be wonderfully stable, perfectly inside its control limits, highly predictable, entirely devoid of special causes, and yet be shipping absolute garbage by the truckload because its stable, natural spread is simply much wider than the customer specifications.
Conversely, you could have a process that is wildly unstable. It is completely out of control. The mean is ping-ponging all over the place. Special causes are hitting it daily. But because the customer specification limits are insanely generous, everything you make still technically passes.
The executives might look at the pass-fail rate and think they have a high-quality system.
Yeah.
But that isn't quality. That's just luck.
Total luck.
The moment the customer tightens the specifications, the chaotic reality of the system will instantly destroy the business. Control limits answer the question. Is the process consistent? Specification limits answer the question. Is the process conforming? Consistency and conformity are two totally different dimensions of performance.
Let's build on your highway analogy from earlier to really visualize this difference. The specification limits are the solid white and yellow lines painted on the asphalt. They define the actual width of the lane. That is the external demand. You must stay between those lines.
The voice of the customer.
Right. Now, the control limits represent the natural, stable swerve of your specific vehicle based on its mechanical alignment and, how loosely you hold the steering wheel. Your car might have a very consistent, predictable swerve. It is perfectly in control.
But if the customer paints a lane that is only 6 feet wide, and your car naturally swerves across 8 feet of asphalt.
It doesn't matter how stable your steering is. You are going to be driving in the ditch.
Or what if your car only swerves 4 feet, which is tighter than the lane, but your alignment is completely shot, and you are driving with your left tires constantly in the grass?
Right.
Your car is perfectly stable. It is highly precise, but you are completely failing the specifications because you aren't centered in the lane. Being consistent absolutely does not mean you are conforming.
Which is why, once we prove our car is steering consistently, we have to formally evaluate its ability to stay in the painted lane. This brings us to process capability. If control charts are the daily operational monitor, capability indices are the long-term report card.
The capability report card. Let's dig into the alphabet soup here, because these ratios are how businesses actually communicate quality internally. We have CP, CPK, PP, and PPK. Let's start with CP, which stands for potential capability.
CP is a simple ratio of space. The numerator is the total tolerance granted by the customer. It's the distance between the upper and lower specification limits, the width of the painted lane. The denominator is the space your process actually consumes, which is defined statistically as 6 standard deviations, or 6 sigma, the width of your car's swerve.
So if a customer gives you a specification window of 4 millimeters and your process naturally spreads across 3 millimeters, your CP is 1.33. The lane is 33% wider than your car.
Exactly. A CP greater than 1.0 means you mathematically have enough space to succeed. But notice the name, potential capability. CP deliberately ignores where the process is actually aimed. It measures the best the process could possibly do if it were perfectly centered exactly in the middle of the specification band.
It tells you that your car is physically narrow enough to fit in the lane, but it ignores the fact that you might be driving half on the shoulder.
Which is why CP by itself is dangerous. To measure the reality of the situation, we need CPK, actual capability. CPK measures the physical headroom between your actual current process mean and the absolute worst side of the specification limits. It aggressively penalizes you for being off-center.
So if your process is tight, but you are aimed right at the edge of the cliff, your CPK plummets. even if your CP looks fantastic.
The gap between these two indices is incredibly diagnostic. If you run a capability report and you see a massive CP, say 2.0, meaning your process is incredibly tight, but your CP key is a disastrous zero point 0.5, the diagnosis is instant. The process is beautifully precise, but it is aimed at the entirely wrong target. It is heavily miscentered.
And the repair for that is usually the cheapest fix in engineering, right?
Yeah.
You don't have to buy new machinery or redesign the software architecture. You literally just re-aim the machine, you adjust the set point, you steer the precise car back into the middle of the lane.
But what happens when you look at the process over a much longer time horizon? KPF and CPA are calculated using the short-term standard deviation. They estimate the variation using the within subgroup noise we talked about earlier. They tell you how good the process is right now, hour to hour, completely ignoring long-term drift.
But processes live in the real world. Over a year, tools grind down. Seasons change the factory temperature. Software databases grow and queries slow down. Minor, undetectable shifts accumulate.
That is where PP and PPK come in. They are the exact same capability ratios, but they use the overall standard deviation computed from all the data across a massive window of time. They include the inherent drift of the system.
I'm looking at these like blood work. I want to diagnose a disease based on the gaps. What if my short-term actual capability, my CPK, is a very healthy 1.33, but my long-term performance, my PPK, is a terrible 0.71?
That is a blaring siren that you have a stability problem wearing a capability disguise. The gap tells you that hour to hour the process is extremely tight, but month to month the center of that tight process is wandering wildly across the specification band. The long-term variance has exploded compared to the short-term variance.
The fix here isn't to buy a more precise machine. The machine is already precise. The fix is to go back to your control charts, track down the special causes that are knocking the aim off every few weeks, and stabilize the system.
Exactly.
So the sequence is really clear. If CPK is low relative to CP, re-aim the system. If P peak is low relative to CP, stabilize the system. Only when all of them are equal and still too low do you undertake the massive capital expense of trying to fundamentally shrink the inherent variance to improve CP.
That diagnostic sequence saves companies millions of dollars in misallocated capital. And we can translate these abstract index numbers into very visceral economic realities by calculating defect rates, usually measured in parts per million, or ppm. If you assume your data follows a normal distribution, a CPK of 1.0 means the nearest specification limit is exactly 3 standard deviations away from your mean.
And the math of the normal curve says that at 3 standard deviations, the tail of the curve crosses the limit, resulting in about 350 defective parts for every million you make on that side. Third down to 350 ppm.
Right.
Which brings us directly to a buzzword that escapes the engineering department and ends up in every corporate boardroom. Six Sigma. When a corporation says they want Six Sigma quality, what does that actually mean mathematically?
Six Sigma is an aggressive design target. It means you intend to engineer a process to be so incredibly precise, so naturally tight, that its CP is 2.0. That means the process spread only consumes half of the granted tolerance. The distance from the mean to the nearest specification limit is literally 6 standard deviations.
If you calculate the tail probability of a normal curve at 6 standard deviations, the defect rate is something like 2 parts per billion. It's virtually 0. But that's not the number people quote. People quote 3.4 defects per million. Where does the 3.4 come from?
It comes from a profoundly pragmatic engineering concession. The architects of Six Sigma, primarily at Motorola, knew that human systems cannot remain perfectly centered forever. They assumed that over the long term, due to tool wear, material changes, and general drift, the mean of any real-world process could shift by up to 1.5 standard deviations off-center.
So you design the system at a CP of 2.06 standard deviations of headroom. But you explicitly concede a 1.5 sigma drift in reality.
Which leaves you with a worst-case CPK of 1.5 on the bad side. The specification limit is now 4.5 standard deviations away from your drifted mean. If you calculate the area under the normal curve beyond 4.5 standard deviations, it equals exactly 3.4 parts per million.
Oh, I see.
Six Sigma is essentially an engineered safety margin. You over-design the precision so heavily that even when the system inevitably drifts, the defect rate remains economically invisible.
Okay, I am going to push back hard on this right now. We are talking about estimating extreme tail probabilities. To get to 3.4 ppm, we are relying on the theoretical area under a curve 4.5 standard deviations out from the center. Does anyone actually trust that math? Real-world data is almost never perfectly symmetrical. If a distribution is even slightly skewed, couldn't that extreme tail be massively thicker than the pure mathematical model predicts?
You are entirely right to be skeptical, and any statistician worth their salt will validate that pushback. These tail probabilities lean incredibly hard on the assumption of absolute normality. If you are operating at a CPK of 1.03 standard deviations, outmoderate non-normality might double your defect rate. It's an error, but it's in the same ballpark. But when you get out to a CPIC of 1.5 or 2.0, the normal model out in the extreme tails is pure extrapolation. Real-world tails are heavy. They are messy.
So the 3.4 ppm number is essentially a useful fiction.
It is a directional compass, not a literal promise. It is mathematically precise enough to allow executives to rank different processes, price out capital improvements, and track progress consistently across divisions. But you should never walk into a room and promise a client a literal 3.4 ppm failure rate based purely on the theoretical math of a normal curve, unless you have actually validated the shape of your extreme tails with massive amounts of empirical data.
That makes perfect sense. Now, everything we've talked about for the last 40 minutes, cutting metal, funnels, marbles, temperature labs, this mathematics was forged in the physical manufacturing world of the 1920s.
Yeah.
But it applies flawlessly to the digital processes we operate today. I want to escape the factory floor entirely and talk about applying SBC to software, web services, and cloud infrastructure.
The conceptual translation from steel to silicon is seamless. In the digital world, the time it takes to compile a software build or the latency of a database API is your variables data. It is continuous.
Okay.
Service level objectives, or SLOs, like the classic 99% of requests must resolve in under 300 milliseconds, are literally just one-sided specification limits and the count of escaped bugs in a release. That is your attributes data.
So the framework is perfectly intact.
Right.
But the physical reality of software introduces some intense mathematical frictions that a CNC lathe doesn't have. Friction number 1, skewed distributions. Software latencies are not normal bell curves.
Not at all. If you machine a 10 millimeter part, the errors can swing equally to 9 millimeters or 11 millimeters. It's symmetrical. But latency data is inherently bounded at 0. A database query cannot respond in negative time.
Right.
However, the time it takes to respond can stretch out infinitely to the right if a server hangs. Latency distributions are heavily right-skewed with long, heavy tails.
If you try to blindly apply Shewhart's 3 sigma control limits to heavily skewed raw latency data, the symmetry of the math will fail. Your lower control limit will often calculate out to a negative number, which is physically impossible, and your upper limit won't stretch far enough to capture the heavy tail, resulting in a flood of false alarms.
The standard resolution in the tech industry is to log transform the data before you chart it. By taking the logarithm of the latencies, you mathematically compress the long tail and pull the skewed distribution back into something resembling a symmetrical bell curve. You run all your SBC math on the log scale and then transform the results back to milliseconds for human readability. Alternatively, teams will abandon mean and standard deviation entirely and state their capability purely in terms of percentiles against the SLO.
Friction number 2 is even more insidious, and it plagues modern tech dashboards. Autocorrelation.
SPC mathematics demands that every data point in your rational subgroup is statistically independent from the others. The random noise affecting marble number 1 shouldn't dictate the random noise affecting marble number 2, but in software, independence is a myth.
Because of caching and load balancing.
Precisely. If a user requests a complex web page, the server might take 200 milliseconds to render it, but the server then caches that rendered page. The very next user who makes the exact same request gets the cached version in 10 milliseconds. The second data point is entirely dependent on the first data point having just occurred. Furthermore, consecutive requests are hitting the exact same server under the exact same CPU load. They move together. This positive autocorrelation completely violates the assumption of independence.
Walk through what that actually does to the math. Why is autocorrelation so destructive to a control chart?
Because consecutive data points are essentially clones of each other, they don't vary much from each other. When you calculate the within subgroup variance, the baseline noise we talked about earlier, the math looks at those cloned cached requests and thinks, wow, this system has almost 0 variance. It is incredibly tight.
It artificially shrinks the estimate of the standard deviation.
Dramatically. And because your standard deviation estimate is artificially tiny, Your upper and lower control limits become suffocatingly tight. They squeeze right up against the center line. Then, a perfectly normal, independent, non-cached request comes in at 250 milliseconds. It is completely healthy baseline behavior, but because your control limits were artificially crushed by the cached data, that point blows right past the upper limit. Your dashboard flashes red, pagers go off, and you have manufactured a false alarm.
You end up with a dashboard that cries wolf every 10 minutes. Engineers learn to ignore it, which is the definition of blindness. How do you solve autocorrelation?
The simplest method is to space out your sampling. Instead of grabbing 5 consecutive requests, you grab 1 request every minute, allowing enough time for the dependent system state to decay. The more advanced method, used in high-frequency trading and massive tech platforms, is to build a time series predictive model like an ARIMA model. You use the model to predict the next point based on the autocorrelation. Then you don't chart the raw data, you chart the residuals, the errors of the model. Because the model accounts for the dependence, the residuals are perfectly independent and SPC math works flawlessly on them.
That is brilliant. You chart the surprises, not the data. The final friction in software is definition drift. In 1924, a defective steel shaft meant it was cracked or out of tolerance. That definition doesn't change. But in software, the definition of a failed build is completely fluid.
A failed build changes its meaning the minute an engineering lead decides to quarantine a suite of flaky integration tests. It changes the minute someone alters the automatic retry policy on a network call. Yesterday, a network timeout failed the build. Today, the system invisibly retries 3 times and passes.
The baseline of the system shifts purely because of human policy, not physics.
And engineering teams manufacture their own false signals constantly by failing to acknowledge this. They alter the retry logic, the success rate shoots up, and they leave the historical control limits on the chart. The chart screams that a massive special cause is happening, but all that happened was a definition change. The baseline isn't a static historical artifact. It is a living entity tied to the current operational definition of the process. If you change the definition, you must sever the data, recompute the limits from scratch, and start a new baseline.
When you look at the modern tech landscape, and you look at frameworks like the DORA metrics that every CTO obsesses over deployment frequency, lead time for changes, change failure rate, time to restore service, if you peel back the silicon veneer, these are literally just throughput, cycle time, and defect rate. Tech companies are spending millions on observability tools to track concepts that are waiting to be put into a century-old Shewhart control chart. The physics of process management are identical. We are just operating at the speed of light instead of the speed of a lathe.
It proves that the fundamental nature of variation is universal.
Which brings us to how we actually live this out day to day. The ultimate takeaway of this deep dive is a continuous improvement loop that never stops.
You monitor the process constantly with your control charts to detect special causes. When a point falls outside the limits, you investigate locally, find the assignable event, and remove it to stabilize the process. Once the process is demonstrably stable, you assess its capability against the customer's specifications using CP and CPK.
If it's not capable, you improve it. You recenter the mean first because it's cheap and easy. Then, if necessary, you undertake the hard management work of fundamentally redesigning the system to reduce the inherent common cause variance.
And once you redesign it, the system has changed. So you recompute your limits, establish the new baseline, and you repeat the loop forever. Monitor, stabilize, assess, improve, recompute.
It is a profoundly elegant system for making sense of chaos. But I want to leave you, the listener, with one final provocative thought. It's something that wasn't explicitly spelled out in the core equations, but it casts a shadow over absolutely every single data point we've discussed today. It is the observer effect of process engineering, measurement system fidelity.
This is the invisible trapdoor under every capability study.
We have spent an hour talking about how to measure the variation of a process. But every single number you collect, every dot you plot on a beautiful control chart is not just the process. It is actually a combination of 2 things. It is the true physical variation of the process itself, PLUS, the inherent variation of the tool you are using to measure it. The mathematical reality is that the variance you observe on your dashboard equals the variance of the process plus the variance of the measurement system.
Think about the implications of that equation. What happens if your machining process is perfectly fine, but the micrometer the operator is using to measure the parts is physically loose and wobbles? What happens if your software deployment pipeline is perfectly stable, but the timestamping gauge in your logging infrastructure is experiencing microscopic clock drift?
It generates fake chaos. Your actual physical process is humming along perfectly. The marbles are hitting the target. But your ruler is made of rubber. The ruler expands and contracts, injecting massive amounts of fake baseline noise into your data.
And because you trust the data, you look at the chart, you see a massive spread, and you calculate a terrible CPK. You assume the process is failing.
If you are a manager listening to this, you might authorize hundreds of thousands of dollars in capital expenditure, or pull a dozen software engineers off feature work for a month, trying to fix a process variance problem that literally does not exist in the real world. The variance only exists inside the measurement system.
Before you attempt any high-stakes capability claim, before you boast to a client about achieving Six Sigma, you have to run a secondary statistical analysis, often called a gauge R&R, to validate the precision of your tools. You have to ask a clarifying question. Can I even trust the ruler I am measuring reality with?
The very act of observation has its own variation. You don't just have to stabilize the process, you have to prove the stability of the lens you are viewing it through. Until you isolate the noise of your tools from the noise of your system, you aren't managing a process. You're just reacting to the muddy waters of your own data. The next time you feel the urge to tamper with a fluctuating system, check your ruler first.